First lecture of Mr. Panagiotis Tsounakis, who's going to talk about a very interesting topic, quantum, 2.0, computing, and more. Mr. Tsounakis, please.
Thank you. Good morning, everybody. You'll see a lot of slides in this presentation, but I'm not going to stick to all of them. I'm going to show the basic things. Basically, we're going to have a bird's eye view on the quantum way of processing information, because we don't have time for this topic that has grown excessively in the last decades so as to become a discipline of its own, and it involves physics, computer science, mathematics, engineering, and more. So I'm going to have a small introduction, and then I'm going to talk about computer memory and registers, and gates and the gates implementation. in computing. We're going to see classical computing and quantum computing in parallel so that we may understand what's different, what's similar, and how the quantum way of processing information works. We're going to see how we detect errors in computation and correct them. We're going to probably skip computability and complexity because we don't have enough time. We're going to see the difficulties of classical processing of information, which is a main reason to get involved in quantum computing. And we're going to talk about communication networks and the quantum internet. And we're going to see why quantum information processing is superior. It's better than classical in specific cases that deserve this special way of processing. And here we conclude the technical section of the talk, and then the last 4 sections are more informative. They are like narrative about what's going on worldwide in the quantum information processing landscape, the prospects. We're going to see some technology examples, quantum technology examples from the future, and we're going to present some things about quantum educational presentations of quantum computing so that you may have access to more material, and we'll conclude with selected recent results, events, and initiatives. I don't know if you're going to get the slides. If you're going to get the slides, almost all results and conclusions are documented, so you can look them up. So I'm going to fly and first explain why are we talking about 2.0 quantum technology. This is the second generation of quantum technology. You heard some things about the first generation, which you can see at the left of the screen yesterday. So there's plenty of room down there, as Feynman said. And the first wave, the first generation of quantum technology involved quantum phenomena in the microcosmos, but in populations of particles, billions or trillions of particles were involved, so that the classical transistor or laser or microwave oven or microwave link, communication link worked. But now, with the second generation of quantum technology, we have the capacity to operate on individual particles, on individual wave functions. And that is a very big scaling because we can do more efficient information processing. You see, we talked about entanglement last night, and at the middle of the right part of the screen, you can see an entanglement picture, which involves individual particles that are entangled, and this is a photograph. So, what about information? If we're going to talk about information processing, we have to remember what information is, and as the picture suggests, what you know as classical information, bits, bytes, all the terms you are used to when using a classical computer, your laptop or your mobile phone or even your smart TV. Classical information is a special case of quantum information. Quantum information encompasses classical bits, so we have a generalization of the well-known classical bit. Bit is short for binary digit, so it's like a switch. You have a physical system and you can turn it on or off. You have a light and you can light up or have it shut. So it's a physical system that can be in one of two distinct states always. always you will find it in one of two distinct states. The quantum bit now is described by a vector, and you see a vector on the right side of the picture, and a vector can be analyzed in x and y axis in its basis vectors. So it is a superposition or a linear combination of the two base vectors. And that symbol's down with a 0, and the symbol, that's ket 0 and ket 1. That's nothing extraterrestrial. It's just the way that physics prefer, with a Dirac notation, to represent vectors. So it's actually a shorthand. It's nothing new. It's just a vector, an ordinary vector. So what about information processing? Two separate things we can see. We can have computation, and computation involves inserting data in one computer, and then there's an evolutionary process of this information. So the information gets put inside the computer and it evolves. Computation is done, and then we extract the output data, the result of the computation, from the same computer. So you put something in and you get something different out. It's the result of your computation. You put 1 and 2, and you want to compute the sum of them, and you get out 3. But we can have also communication of information. Now, we insert input data into the computer, or more generally a telecommunication systems like a mobile phone, and then the computer or the device transmits the input data to a different place through a telecommunication network. And you get the same data. The task is to get the same data without alterations at a remote site at a later time. So these are the two main functions in information processing. Now, we will show in parallel classical and quantum aspects of information processing. And we already said that you have a classical bit. You can always look it, and if you look it once, that's enough. It's set to 0 or it's set to 1, one of the two distinct states a binary digit can be, and that's all. But if you have a quantum bit, then you have to measure it thousands of times and get the statistics of the result so as to conclude if the vector is closer to the horizontal axis or to the vertical axis that represent the two distinct binary values that you can get out of a qubit. The quantum bit is a superposition as long as the quantum evolution, the computation is evolving. But at the end, the result is classical information. We are living in a classical world. We can only perceive classical information. We are not quantum entities. So even if we have a quantum computer or a quantum network, we will input classical information. All the magic is done inside, and then we get out classical information, which is the result of the computation we want. But in the quantum computing realm, we have to do the same evolution thousands of times and then get the statistics, get the results that come out from quantum probability, as Professor Andoniou explained yesterday. So this is a qubit. It's in a superposition. It goes like that. It evolves, and it might rotate. At the end, we will measure it, and we will get either ket 0 or ket 1. Another difference between classical and quantum bits is that classical bits the systems we use and the technology we use to represent classical bits are stable. I mean, you store a bit and it's there for seconds, hours, days, even years if you store it in a CD-ROM or a hard disk. But it's not as easy with quantum bits because there is a phenomenon, a quantum phenomenon, decoherence, that has the effect to wash out the quantum properties of the system as time flows. So you have a perfect quantum wave function, quantum state, and after some time it degrades and it's not a qubit anymore. It's like the flowers if you leave it in the vase after several hours or days. So what's the effect of quantum decoherence? When decoherence occurs, the landscape is blurred, and it's like the picture in the middle, where we had a qubit, but we're not exactly certain after some time where exactly the vector is. We don't know if it's the red or the blue or the green vector. And it might be any of these vectors, and there are probabilities for each position of the vector. And that probability is classical probability. It's not quantum probability anymore, and we don't have the benefits of quantum information processing when we reach this state. It's called the mixed state in quantum terminology, and it's a degraded wave function that we cannot exploit anymore for computation. So, if we have a decoherence, then the quantum vector can have some errors. Bad things can happen to it. It might rotate, and that is the case down on the left corner. So the face of the vector changes. This is a representation of the vector in block Poincare sphere. It's a notation that is used many times in quantum realm. What you have to remember from this slide is that when a vector rotates, the face changes, and that may cause an error, and is really a very nice property, the face of the vector we use in quantum computation, and if it's altered, then we may get errors in the computation. If decoherence occurs, the vector might also shrink, and the more it shrinks, the more difficult it is to distinguish it with other vectors. So you can have a shrinking, you can have a rotation, or you can have both of these errors, and all these cause problems and invalidate the results of the computation. I will skip this one. Mr. Voulias, will they get the slides? The students? Yes? Okay. So in the Kimmo said. So you're going to get the slides. So if you want to play around with the coherence, this slide shows at the bottom a URL, and you can have an interactive educational animation of quantum decoherence. And there's a step-by-step procedure that you can explain. So, what about memory and registers? We have bits on the left, classical bits. When I'm talking about a bit, especially mathematicians think of an abstract mathematical entity. But we live in the real world, and unless you have a physical system to store information, you don't have a bit, you don't have information. As Ralph Landauer said, information is physical. So, even if you think mathematics in your head, you store information inside your brain, inside your neurons. So, we always have a physical system to store classical bit or a quantum bit. And if we have a group of bits, an ordered group of bits, because order matters, both in classical and in quantum information, then we call this n-tuple a register. A classical register is like an ordered group of switches. You can individually put each switch in the on or off position. But if we have a quantum register, it's an ordered tuple of qubits, but things may get more complicated, more rich in this time, because whereas in the left the classical bits are described by a Cartesian product of the states of the bits, in the right we have a tensor product. Well, you might not have heard of tensor calculus. Tensors are generalizations of matrices, which are generalizations of vectors, which are generalizations of scalars. We can have a physical quantity that's described by one number, that's a scalar. We might need components, and that's a vector. And we might arrange these components not horizontally or vertically, but both, as a table, as a matrix. If you have more indices, not like a cube, then you have a tensor. I'm simplifying, I'm oversimplifying just to get you the general picture. Now, what's different in a classical or quantum and the quantum register? There's entanglement in quantum register. That means that there are correlations, there might be correlations among quantum bits, so that changes in one qubit are not only in one qubit. They might affect other qubits. That's not the case in the classical case. You can tweak individual classical bits, but when entanglement is present, if you do something to one qubit, another qubit might get altered. So that's a very big difference, and we utilize it for quantum computing. Now let's talk about gates. What are gates? Well, gates are the way computer scientists name mathematical operators. A gate does an operation. It implements an operator. So we have a classical gate on the left. So we input two classical bits, and we get the result of a function that the gate calculates. In the quantum case, it's a little bit different. It's more general. You get one or more qubits inside, and you transform it inside the gate, and you put it outside on the other side. But you can always go back. Almost all gates we utilize in quantum computing are reversible, meaning you can do the reverse operation. You can start with the output and get back to the input. Such a thing is not always possible in the classical computing case. So, some notation. In the classical case, we have Boolean gates, we have Boolean logic, as we will see. So we have symbols, and we describe them with a truth table. What's a truth table? You just have a column for the input and a column for the output, and you have a gate symbol individually represented. So what does a negation do in a classical bit? A classical bit can be only in two states, a 0 or a 1. So if the input is 0 and you put it through the NOT gate, it gets to the 1 state. If you input 1, you get out 0. Now, you can have the similar effect with a quantum NOT gate, which is presented on the right, but in this case, you have a matrix, a unitary matrix, as we say. It has some specific properties. So what's the gate operation? You multiply the matrix with a vector, and you get the new vector as a result. So you start with ket 0, and you have the x gate, the x matrix multiplied with a ket 0, so you get a ket 1. If you multiply the x gate with ket 1, you get a ket 0. And if you get a general qubit, a general description of a qubit, which is a linear combination, A times ket 0 plus B times ket 1, and you negate this one, you get the components of the vector flipped. AB goes to BA. Now we have lots of gates. Another gate is control node. What does it do? And we will I have to say a few things about notation. In quantum computing, we use horizontal lines to describe qubits. So on the right, under the quantum gate symbol, you see two horizontal lines, and there are two qubits. So what does this unitary matrix that corresponds to the control gate operation do? If the upper qubit is set to 1, it flips the value of the lower qubit. So it does the flipping only sometimes. It's a conditional gate. It has 2 qubits as input and gets 2 qubits as output. There's not a classical gate like that, a simple gate, but we can always simulate it. And here's how we do it with the red arrows. You see the classical operation of the fan-out gate. What's a fan-out gate? In classical circuits, we have the value of a bit, and we want it to send it to multiple destinations, so that in many places of the computer, the same value is sent. Some of the basic gates are the logical AND gates. A logical AND gate is a gate that gives the result of 1 if both inputs are 1. And here we have the classical case on the left and the quantum case, also named the Toffoli gate, on the right. And you can see that if you set, when you have a quantum conditional gates, the qubits with a small dot are called control qubits because they control the operation of the gate, and the big circle is the target qubit because it's the result of the computation we want. So if you set the target bit to 0, then at the truth table you see that you can have the AND gate, the classical gate implementation with a quantum gate, Toffoli gate. So I'm using all this correspondence to show that anything you can do classically is a special case of quantum information processing. And then we have the OR function. If you have 2 qubits, the OR function gives 1 if any of the 2 qubit input bits are 1. So there's a classical gate for that, a Boolean gate, but not a quantum one. But we can simulate it. We can construct a circuit, which is a gate composition in the quantum realm, and implement the quantum OR gate, and this is shown on the right. Don't worry if you don't get anything here. You can look it up later, and you do the calculations of yourself, and you verify. Don't believe me, verify what I'm saying, and you'll find it correct. So there's also another Boolean function, the exclusive OR gate, which gives a 1 if either of the bits is 1 but not both. And there are gates that are only valid and meaningful in the quantum world. The Pauli X gate is both valid in the classic and quantum world, but the Pauli Z and Y gates in the middle and at the bottom of the screen are only valid in the quantum realm because what they do, they rotate the vector of the qubit. In the classical bit case, we don't have a vector. There is no such notion as rotation. You can only set it to 1 or 0, and you can flip it, change the 0 to 1, or vice versa. But here, we can have more different ways to alter the vector. We can rotate it. Another quantum-only gate is the Hadamard gate. And what does this one do? It puts a qubit in a superposition. And it's a very useful and we always use this gate. Now, how do we extract information from qubits? We have to go from the quantum realm to the classical, back to the classical realm. So we use a quantum measurement. Mathematically, a quantum measurement is a projection operator. It ends the superposition state and gives a result. It collapses, as they say, the wave function to either ket 0 or ket 1. And now, if we want to be trustworthy in what we measure, we have to repeat the same evolution and finally measurement thousands of times, and then we'll get the statistics, how many times it was ket 0 or ket 1, and then we can extract the information we want. I will not elaborate on the details of the measurement. I don't have time for this, actually. A similar operation is the quantum reset. You have a quantum circuit, a composition of quantum gates. You do your computation, and then your problem is solved, and you want to reset the circuit. There's a projection operator that whatever state a qubit was in, you don't care. You just put it back on the ket 0 position, which is this vector 1, 0. And you can have also the quantum set operation. How do you do that? Whatever the qubit was, you reset it, and then you flip it. So you set it to ket 1. It's also a projector operator, and at the low right corner, I show you the way to do it with a quantum circuit. So gates are simple operations. Circuits are composite operations. They are like function composition mathematically. So you can compose classical gates and fix a classical circuit, or you can compose quantum gates and fix a quantum circuit. And on the left, we see a classical circuit that inputs A and B, 2 qubits. And at the end, at the right side, in the center of the slide, we get A XOR B. This is the XOR gate implementation, which is performed through OR, AND, and NOT gates. AND, OR, NOT are 3 very basic classical gates. 2 out of 3 of them are universal, meaning you can compose any Boolean function using 2 out of 3 of these gates. So they are called universal gates. At the right, you see a quantum circuit. Now there's more complex notation. When you have an horizontal single line, it's a qubit. When you have a double line, it's a classical bit that gets to exist because of the measurement of a qubit. You can't have a classical bit unless you measure a qubit, and this is what the 2 black schemes at the right show. It's a measurement operation symbol. So you put a lot of quantum gates to do your computation, and at the end you measure the qubits, and the bit pattern, the classical bit pattern you get out of measuring all the qubits you want is the result of your computation. So one thing about differences in classical and quantum classical computing, as is usually done, is the reversibility of computations. You can also have reversible computations in the classical world, but we don't usually do that. If we have an AND or an OR gate, then this is not reversible. Meaning, if I give you the output of an AND gate, if it's 1, you know the input. An AND gate is 1 if both inputs are 1. But if it's a 0, you don't know what caused it to be a 0. It can be in any of the 3 cases on the left truth table, the 3 first lines, okay? So it's not a reversible operation. You cannot go from the result to the input. Likewise for the OR function. But if you have a NOT gate, if you get the result of a 0, you know that it was input a 1. If the result is 1, you know it was input a 0. So that's a different case. You can always convert an irreversible gate like AND or any other composite function to a reversible one using an auxiliary bit, and that's the way to do it. I'm not going to elaborate on that, but if you examine carefully the truth table, you'll find that I'm speaking the truth. Now about gate implementation. How do we implement gates in the classical or in the quantum world? What are the technologies used? Well, in the classical world, we have transistors, and we combine transistors into integrated systems, integrated circuits, chips. We can also have fiber optics to carry around classical bits. We can have wireless communications. There are more technologies in the quantum realm. It is still a very evolving landscape in the quantum. Various technologies have been established in the classical world. There is still technology competition, fierce competition of technologies in the quantum world. So we have superconducting junctions to implement qubits. We can have integrated silicon photonics chips, integrated circuits which have fiber optics inside, and they use photons combined with silicon. And we can have lasers, we can have lots of other technologies called atoms and stuff like that. Some things about digital circuits. These are historical events. I will not stay with this. First integrated circuit in 1951. And, well, if you compare the classical computing evolution with quantum computing evolution, classical computers evolved from the ENIAC of 1945 till today. It's like in the quantum world is like being in the 1960s compared to the classical technology evolution. We still have a long way to go, but technology is maturing, and it's maturing rapidly. So we can have classical circuits to implement arithmetic operations with Boolean algebra. Boolean algebra is the basis, the mathematical foundation of classical circuits. And this is a circuit that adds 2 binary digits and produces the sum and the possible carry. Because if you have input 1 and 1, this is 2. But you cannot represent number 2 with a single binary digit. You need at least 2. So you have to move a carry to the most significant position. And now you see another half adder in the classical and in the quantum case. What does a classical and half adder do? input 2 bits, you get a carry and a sum. That's all. Now you see how we can produce an example of a Boolean AND function using the IBM cloud to access a quantum computer on the cloud and program a quantum circuit on this cloud. And here you see the statistics of the results. The way I combine the upper 2 qubits and process them with the gates corresponds only to the blue combinations, meaning that there is no way that both inputs are 0 and then 1 is output. It never happens. It has no presence in the quantum statistics. Blue bars are what happens if I run this circuit thousands of times and calculate the results. So this is the implementation of an AND gate by a quantum circuit. Similar example with the OR gate, or the OR gate squared. I mean, I applied twice on the same qubits. Now, to distinguish between quantum computers and classical computers, we have to review how computation is done. How does a classical computer calculate? With the circuits that comprise of gates. Well, there are 3 things a classical computer does. It does addition. It can compare 2-bit patterns. And it can assign, I mean, it can copy a group of bits from one place to another. These 3 actions are all you need to do any computing. Anything this laptop does can be resolved to these 3 bullets. Now, in the quantum realm, computation is different. We can use entanglement. We entangle bits, and remember the chains in the quantum register. You can use entanglement to steer a qubit. You can alter 1 qubit by applying a quantum operation to a different qubit that's entangled to the first qubit. That's not possible in the classical world. It's a purely quantum phenomenon. Then, one major difference is that qubits are described by wave functions, and waves interfere. So we have constructive and destructive interference, and we utilize interference in the quantum evolution of many qubits to produce the result we want. And the way to do it is to amplify these states that are desirable, that lead us towards the result we want. Let's see another example that shows the difference between the classical and the quantum world. I want to swap 2 bits. I mean, one is here in the memory, the other is there, and I want to just exchange the positions. To do that in a classical memory, a random access memory, I need to use an auxiliary 3rd place to store one of the bits and then to swap them. And this is the sequence. This is a case of the pigeonhole principle. You can't have 2 pigeons in one hole. Only 1 pigeon in each hole. But in the quantum realm, we have the swap gate, which is a circuit composition of 3 CNOT gates. And there, you can swap 2 qubits on the fly without using a 3rd physical system to store information. How is this possible? Quantum entanglement. The CNOT gate entangles quantum bits, and we use 3 times this CNOT gate. So, how do we compute, we input the classical information, it gets encoded as vectors, as qubits, and then we apply gates, we measure the qubits, and we extract the classical bits as the result of the measurement. Here I show computer architectures. The classical von Neumann architecture on the left, and the quantum architecture, the quantum processing unit, or QPU, whereas in the classical world we have the CPU. So we have a processor and the main memory, and we have control logic inside the processor and the registers and the computational circuits that implement all the Boolean algebra operations on the qubits, and that's classical computing. On the quantum case, we have control logic, we input classical, we have drivers, and then we convert the classical bits to quantum bits. Then we have specific systems to implement the quantum gates via the technology that is implemented in the system, and then we have to extract the result. And there are references that you can, at the bottom, you can read more details on this subject. So much about processor architecture. You see on the right a schematic of a quantum computer, and at the center of the screen, we highlight the classical quantum border. I mean, what's inside the quantum processor works in most technologies, called atoms, superconducting qubits, etc., in temperatures near absolute zero, millikelvin temperatures. And this is our way, our main way, to avoid decoherence, to extend the life of the qubits, to shield them from noise caused by high temperatures that will make the wave function decohere. So, qubits and the control and readout electronics are very cold. And outside, there is the classical hardware and software that is necessary to have an integrated quantum computer. This is an example of a layout of a quantum computer of IBM. It has 156 qubits. Nowadays, we have quantum computers that each one has 100, 200, maybe more, maybe less qubits. And this is in contrast with classical computer, where we talk about megabytes, gigabytes, millions, billions, trillions of bits can be stored and processed in a classical computer. Only a few hundred qubits can be processed by a quantum computer. So this is a topology, how qubits are connected logically. And these are some details on the resources that are used in quantum computers. I have to skip this. Now I've already talked a little bit about errors. In the classical realm, some bits may be flipped, the red ones. So that's the only kind of error we can have. But if you have a vector, it gets rotated, it gets smaller, and these are the quantum errors. How do we deal with quantum errors? Peter Shor, famous for its error-correcting code, years ago presented a quantum circuit that can deal with both bit flipping, qubit flipping, or defacing, phasing errors. At what cost? It uses 2, 4, 6, 8, 9 qubits to build one logical qubit. So this code has a very large overhead. You need 10 physical systems, 9 physical systems, 9 qubits, to get one logical qubit, meaning a system that is fault tolerant on errors. IBM will try to build the world's first large-scale fault-tolerant quantum computing by 2029. They are on their way to do so. So a new term arrives, logical processing unit, meaning a quantum processor that works with logical qubits. Other companies have their own roadmaps on this way too, with different technologies. There's a fierce competition among companies, and it's not clear at this time which is the winning technology, but some are more advanced than others. And there are researchers that follow a different path. Instead of using a code with an overhead, getting a logical qubit out of 10 physical qubits, they did some research work, and they produced qubits that stay coherent without decoherence for 70 seconds. That's a very long time for qubits. I mean, best qubit coherence times since now were in the order of milliseconds, not seconds. Computability and complexity. This is a reference slide. You can read the details on your own. I will just say that when we talk about computational complexity of problems, we deal with how difficulty of the problem is related to the input size. How difficult is computationally hard or easy is a problem depending on the size of the input. Computability is a different thing. Not everything can be computed. Not all problems have solutions. Those that can have a solution are the computable subset that we deal with. Difficulties of classical processing. There are lots of challenges and there are remedies. The heat in the classical computers does not allow us to evolve them beyond certain points. There is the Moore's law, that empirical law that we will explain later. We have challenges like vast data sets. Nowadays, lots and lots of bits are produced every day, and we might have problem not only to process them, but also to store them. Some time ago, somebody told me that one of the biggest problems in CERN was that they could not buy hard disks fast enough to store the data they produced. And sometimes there are physics experiments, produced petabytes of data, and the results are published years later because you have to process all of them, and it's not an easy thing. Recycling the materials is also another problem. There are various remedies, technological improvements of this. Moore's law is an empirical law stated by the late Gordon Moore, one of Intel's founders. And what it basically says that the number of transistors on microchip doubles every 2 years, and the cost is cut in half. From 1970 to this decade, this law holds. But now we have made classical integrated circuits very dense, billions or even trillions of transistors are stored in an area like this, we have reached nanometer distances among transistors, and we cannot scale them down. We cannot squeeze transistors anymore without being exposed to quantum phenomena. And then classical processing will no longer work. So we are near the limits of technology for classical integrated circuits, and there are various workarounds, and quantum computing is one of them for certain problems. Now, the essence of quantum computing is the quantum algorithms. Quantum circuits, the sequences of gates, implement algorithms. So there are various algorithms. I present here the more well-known algorithms, like Grover's algorithm that can find the needle in the haystack more efficiently than any classical algorithm we know. And there are other toy algorithms like Deutsch or Deutsch-Jozsa algorithm, which are not doing something useful at a practical level, but someone who wants to study quantum algorithms have to use these algorithms as starting points so as to understand the concepts behind quantum algorithms. They use the notion of oracles. We have a query gate or a query circuit. We can input some bits or qubits and get a guess about the output. We can, using the algorithms, you can utilize the constructive or destructive interference among wave functions. You will hear that being told as phase kickback. And what is the point, what is the major issue that we're trying to achieve? As Professor Scott Aronson says, the quantum speedups, the best results, the improvement we can expect from quantum algorithms, depend on choreographing interference. We have to guide interference so that we concentrate the amplitude of the wave function to the right answer. Evolve a pattern, a group of qubits, so that at the end of the evolution, when the qubits are measured, they produce the answer to the problem, the function value of the inputs we wanted. So let's switch context, talk about communication networks. You all know classical networks. You're on the internet. The internet is the global network that transfers classical bits here and there. It's not the web. If you surf the web, you use an application built on top of the internet. There are various similarities and differences with classical and quantum computer. It's a packet switch network, classical internet. We pack bits together and send them here and there. And it's a different thing with the quantum network because we use entanglement as a resource and spend it in order to teleport a wave function to another place. You will hear about qubit teleportation. Bear in mind that no physical system is teleported like Star Trek, okay? It's just information that gets teleported. I mean, I have qubits here, I have qubits on a different place, and when the teleportation protocol concludes, a physical system, a qubit on the destination side, has the wave function that a qubit had in the starting point. It doesn't have it anymore. You cannot clone qubits. You just teleport them. If I put the qubit here, it's no longer there. It's not the same with classical bits. I can always copy bits, okay? So there are various constraints, time constraints also, because qubits decohere, and you have to transport it fast enough so that they don't decohere. But if you have a classical network, then if something wrong happens during transmission, you just retransmit. Qubits are, the classical bits are still there. So how does the quantum internet look? It coexists, and it needs, as a prerequisite, the classical internet. It works with entanglement distribution on top of the existing internet. So if we're talking about quantum internet, the classical internet is not going to disappear. But as the World Wide Web works on top of the internet, the quantum internet will work on top of the classical today's internet. So here you see quantum routers, machines in intermediate points. You see classical links. You see quantum links. And there are methods, mathematical methods like the teleportation protocols to send qubits around and mosquitoes around. How about quantum communications in Europe? There are QRQCI is a research project in Europe that implements quantum networking in Europe. Greece is part of this network, of this research project. The main application is quantum key distribution, quantum cryptography. Cryptography is safer than the classical way. What about quantum computers and networks? Well, quantum networking, one of the uses besides cryptography is to facilitate distributed quantum computing. And we already saw that a couple of years ago when IBM built separate quantum processing units and interconnected them with links so that they operate as a bigger computer. Like you have a classical processor with 4, 8, or 12 cores, okay? So you multiply the processing power by interconnecting quantum processing units among them. And here are some distributed quantum chips, interconnected. These two chips on the left, quantum processing units, can work as a single quantum computer. Now, there are protocols and research results that enable us to teleport a wave function, a qubit, between a photon and an atom. Why is this useful? Qubits inside quantum computers live in cold atoms or semiconductor devices, but if we want to transfer qubits around, we usually do it with photons. It's a different physical system, and we can untangle different physical systems between them, and we can extend the network this way. If you want to build your own quantum network and have enough money, you can go to Aliro Quantum, a company in the USA, and tell them to build you a quantum network, just like you go to the Greek PTT or Vodafone and say, I want a classical network. It's already commercially available. If you want to find minerals, you can use quantum sensing. Quantum information processing is not only about computing. We have computing, we have networking, we have sensing, we have quantum systems simulation that are the main four pillars of quantum information processing. So there are quantum sensors sensitive enough that can help you find minerals on the mountains. Now, if I have a little time, I will try to explain why quantum information processing is expected to be supreme. There are lots of different difficult problems that we cannot deal with classical computers. Their computational complexity is so high that we might have to run classical algorithms for years or centuries to solve these problems in large scales. So we try to build technology that will allow us to build systems and solve this in a very short time. Now, quantum supremacy or quantum advantage is a term widely used, coined by Professor John Preskill some years ago. And what does it mean? Well, we have quantum supremacy when a quantum computer outperforms by far the fastest classical supercomputer on a problem. And there are lots of disputes among big computer vendors about this stuff. It started with the solving of staged problems with no practical use, just to showcase that there is something that a quantum computer can do more efficiently than a classical computer. But, warning, if I show that a quantum computer solves a problem better than the fastest supercomputer, it does not mean that there is no classical algorithm that could solve the problem even better than the quantum computer. There might be a classical algorithm, but nobody has composed it, has discovered it yet. We cannot exclude that. So we have to keep that in mind. The building of a rigorous mathematical proof that there is no way to do the solution faster is a different thing, much more difficult. Now I show you some cases of quantum supremacy. First claims started back in 2019, recently in 2023, and there are cases from Google in 2020 for the first quantum simulation of a chemical reaction. Cases of quantum supremacy for practical solutions. See this on the left, the curves. We want to exploit the concept of the line, the area on the right side, something that is big enough so that it deserves the overhead of quantum computing because it can be solved faster than a classical computer. We are not interested in solving problems on the start of the axis because a classical computer can do it better than a quantum. Quantum computing is not for everything. It's for special cases, difficult problems that we cannot solve classically. Now there's a table of recent claims of quantum supremacy. This is a 2024 table result. And far more, people are getting bored of quarreling about quantum supremacy, so they try to standardize the supremacy or advantage benchmark. So there are operational definitions and various methods that they have to agree so that we can, when somebody claims that there is a quantum advantage, we can have a benchmark and say, okay, this is genuine advantage or not. And so we go to the prospects of quantum information processing. And here you see some scientific areas, and you can see how long it would take and how many qubits we would need to solve problems. On the upper right hand, quantum chemistry. This is hard. You may need millions of qubits, and it could take you thousands of years to solve the problems. So we start by chasing problems on the lower left corner. These are the easiest, and we start from that. There are roadmaps on the development of quantum computers. IBM has one and has been consistent in its roadmap for several years. What are the red text in the middle of the picture? They already started building multiprocessors, quantum multiprocessors, by networking, by interconnecting individual quantum processors. So other vendors have their own roadmaps, so you can check the competition and how, if one presents a roadmap, all competitors have to present a roadmap so that they don't seem that they don't have anything. So there are bright prospects for quantum information at the global level. There are applications from the future that we've never seen before. Nobel Prizes have been mentioned yesterday. There's a lot of money in this business, both public, government, and private funding. And there are mobilizations of governments, of the EU, of universities, and industry. And one major front is the education, the quantum education, because we can build quantum computers easily than building computer experts in quantum computing. There are dangers. If you promise and promise and promise things, then you might promise more than you may deliver, and that will be a problem. And we've seen that play before in the artificial intelligence case. Most of the technologies and methods and concepts in artificial intelligence were known back in the 1980s and 90s. I was taught as an undergraduate student much of them, many of them. But we didn't have enough data in those days. We didn't have enough computing power, so the mathematics could not be applied at a practical level. And what happened? The winter of AI. Nobody was interested anymore because they could not produce practical results, and funding ended. So if we promise more than we can deliver in quantum, people might get cautious, you know. Is the world ready for quantum computers? Will companies and organizations know how they could benefit? It's something exotic for lots of people, but big companies are trying to get educated in that, and big universities have established departments and studies, program studies in quantum computing and quantum information. For the infrastructure is another matter, maybe similar to problems caused by AI, excessive use of energy. So, what's the prospect? If we suppose that mathematicians will answer all theoretical questions and physicists flawlessly implement mathematical models in the lab, engineers demonstrate the technology scales to industrial production, there are different stages of developments. First, you deal with a mathematical level, you build a proof of concept in the lab, and then engineer comes and scales it in industrial production. What else do we need? We need a skilled workforce. What should you read behind this line? Career opportunity. There is a career opportunity no skilled workforce is available. I will show more in the future. But we also need standardization, interoperability, policies, strategy, institutional and regulatory framework. Good thing is that these things advance in a more rapid pace because we know how we did that in the classical computing era. So we get lessons from classical computing development and apply it to quantum computing development. I'm not going to stick on the Nobel Prize for Physics and the breakthrough physics, but there was also a chemistry Nobel, quantum dots. Quantum dots are one of the technologies used to implement quantum computing. It got a Nobel Prize too. So there's a whole quantum ecosystem, lots of billions worldwide, put in the quantum computing business. And this is how innovation grows faster than overall innovation. There are the bars that show how many publications and patents are published each year, and the red one that has to deal with quantum. So, comparing in artificial intelligence and machine learning, I'll stay 1 minute here because the workforce. This is the estimated computer job growth by 2040. So you see, 500,000 people skilled in quantum computer may be needed by 2040. They're not available right now. Would you like to be one of them? And now we see how talents are distributed within quantum ecosystem from each country, statistics. And here we see how many patents are published each year. I'm going to pass through this. This is interesting, the hockey stick principle. It shows how rapidly something is adopted after it's introduced in the market. Well, that's the case with NVIDIA and the computer graphics, the GPUs used in artificial intelligence and other high-performance computing platforms. The small picture is showing how steeply NVIDIA stocks fell when DeepSeek announced that it could do the job at a fraction of the cost of NVIDIA. But we're not expecting that quantum computing adoption will follow the hockey stick principle. Experts predict a more linear growth. Let me conclude with some examples of technology. This is interesting. Some guys build a quantum network from quantum key distribution, secure communication, cryptography. Well, it turned out that technology was so sensitive that you could detect earthquakes or vibrations from trucks or trains near the path of the fiber optic cable. Very sensitive technology, because it has to be very sensitive because you send one photon and you have to detect one photon. Classical communication, you send trillions of photons, you have to detect them. Much simpler implementation. How can we build a qubit? We trap an electron inside solidified neon. One technology to implement a qubit. One electron, trapping one electron. Well, not trivial. You can read the details, the reference on the bottom of the screen. Transmitting information through existing telecommunication cables. The Earth is wrapped around with fiber optic cables many times. But initially, quantum systems used photon at a different frequency than the one suitable for commercial available fiber optics? Well, they solved this problem because they changed the frequency of the photons so that quantum communication may use existing fiber. Huge improvement. You don't have to lay out new fiber optics through the Pacific to send the qubit from USA to Japan. You can use existing cables. Some details about these things. Finally, some results in the mathematical framework or a technology. And I'm going to briefly show quantum information is not only about computing. It can be also used as a cosmological tool. We have quantum clocks, much more accurate than the best atomic clocks in the world. There's a new field in physics called quantum thermodynamics. You can learn it about, you can read about it in the reference. So, quantum information is a glue. It can be used to link concepts as different as space-time, gravity, entropy, quantum field theory, quantum information, and entanglement. For all this, I claim there are scientific results published in scientific journals. One example of randomness equification using quantum supremacy. This is interesting. When the inventors started building quantum computers, it was ad hoc. They would build the device as it suited them in their own lab. But now they're getting standardized. A standard 19-inch rack that can host classical computers can also host quantum computers. So that quantum computers can be integrated in existing commercially available data centers and not be as exotic as at the right of the picture. The right of the picture, I show you how ENIAC was and how a first build of quantum computer was, but on the left you see standardized and more standardization, a 19-inch rack having both the fridge to cool the system near absolute zero and the quantum processing unit. A reference to the exotic Majorana qubits of Microsoft. I don't have time for this, unfortunately. It's very interesting physics. Microsoft had a big problem with that because a couple of years ago they published papers that the results they were not validated. So they retracted the papers from Nature, and it took them 3 years to return with something that actually works. Quantum networking and distributed computing. One of the big, very useful aspects of quantum networking is to multiply the computing power of the small quantum computers by connecting them through the quantum internet. There's also an Australian company that has set to build a quantum processor with 1 million photonic qubits. Hundreds of millions of dollars are invested in this business. Quantum open source and interoperability. Well, our lessons from the classical computing are getting put into action in the quantum realm. People are using open source, open technologies in the quantum realm because everybody needs to be part of this revolution if it's going to be sustainable. Some results about improvement of coherence time. A D-Wave Canadian company has actually recently showed a quantum solution to a practically useful problem, and these are the details. They use quantum annealing, model of computing different from the quantum circuits I showed, but it's not mainstream. Some milestones about this, and we conclude with there is a convergence of quantum computing, quantum information processing, and artificial intelligence. One helps the other. So I have some educational presentations of quantum information, but I don't have the time for that. You will hear from quantum in pictures from Lazaros Arigiolis later, so I don't elaborate on this. Quantum gravity experiments with the quantum processors. The World Quantum Day each year, April 14th. And thank you.
Thank you very much.
I thank you for your patience. It was a long one.
I think we have time for a couple of questions if somebody wants to ask something. Mr. Tsounakis. Yes, please. Give me a sec.
So you mentioned that quantum computers can do certain things, for example, like processing in a way that is more complicated than classical computing, for example, with binary digits compared to how quantum computers work. However, wouldn't that make things more complicated in a way, and that it essentially could make them less efficient in the long run?
Well, quantum way of computing is more complicated than the classical way, or it seems so because we're basically used to the classical way to compute. You have to think it over with a different approach in order to build quantum algorithms. But it's not going to replace classical computing. It's suitable only for certain optimization problems or other problems that you can build efficient quantum algorithms for solving it. Okay?
Okay, I think that we ran out of time. You'll have the chance to talk with the lecturers later.
Yeah,
I think that Professor Antoni wants to make a last comment, and we'll move on to the next presentation. Okay, so thank you very much. Sorry for...
I'll be available.
We start running out of time. And now let's move to the next presentation of Mr. Ernestis Kosmidis. He's going to be talking about quantum games and selected applications.
Ναι, συγγνώμη. Με τα παιχνίδια είναι...
Νομίζω ότι είναι συνδεδεμένο στο free.
Είναι ήδη.
Θέλετε να το κάνουμε επέκταση οθόνης ή...
Ορίστε.
Να το κάνουμε επέκταση οθόνης ή... mirror είναι. Νομίζω καλά είναι.
Τέτοιο δεν υπάρχει επόμενο.
Είχα ζητήσει να μου φέρω.
Το ίντερνετ είναι... Ούτε ναι, άμα έχετε pointer ή ποντίκι, κάτι τέτοιο, κάτι... Δεν έχει ίντερνετ. Δεν πρέπει να έχει ίντερνετ. Ναι, μπορούμε να συνδέσουμε για τα παιχνίδια. Να συνδέσουμε το κινητό μου. Δεν ανοίγω. Αυτό δεν ανοίγω. Κάποια τα παίζει. Okay. Νομίζω εντάξει, μπορούμε να ξεκινήσουμε. Ναι. Νομίζω ναι. So, guys, good morning from me. I'm Anestis Kosmidis. I'm a PhD candidate in the Aristotle University of Thessaloniki, and here is my colleague, Lazaros Sargiolis, who is also a PhD candidate. We'll present you today some selected quantum games in order to see in practice all the quantum concepts you heard about last days, such that superposition, entanglement, and all this. So, firstly, Lazaros Sargiolis will present you about the quantum bits.
A little bit of introduction. Mr. Jounakis said much of this stuff, so will not stay here long. As you remember, classical information measured in bits, 0 or 1, but quantum information, for quantum information we need a vector, okay, a state vector. And of course a basis, 0, ket 0, that symbol there, and ket 1, the other symbol, which are two vectors, two orthogonal vectors. Okay, two orthogonal vectors, and every linear combination of this vector is essentially a quantum state. Okay. Now, let's imagine the same concept with a coin. Okay. If you take a classical coin and you flip it, you can get either tails or head. Okay. So you have two possibilities. Now, let's imagine that we have a quantum coin. What a quantum coin would do in this case? Well, when we observe it, when we see the quantum coin, we will still see heads or tails. But the state of the quantum coin will be described by a vector. So this vector will be maybe in a superposition of the observable states, that is, heads or tails. Okay, so we can imagine it like this. We have the horizontal axis for heads, the vertical axis for tails, and any linear combination of these two vectors. of these two vectors, of these two vectors is a state vector. So when I observe the system, what I do? I see only the heads or tails with a probability that comes from the projection. Okay, if you see the shadow that this little arrow makes in both both axes. Okay, this shadow shows us the probability. So, if we flip a fair quantum coin, okay, we expect to see 50% head and 50% tails. And this is the vector, okay, this is the linear combination that gives us this state that produces these results. Now, if we flip two coins, what we expect? If we have two classical coins, all the combinations we can get is this form. Heads, 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 tails, tails, heads, tails, tails. The same thing is true for quantum coins. Okay, so we can observe heads, 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 tails, tails, heads, and tails, tails. But the state that describe the system of two quantum coins is the linear combination of these four states. So it's this one down there. Okay, it's a linear combination of four states because I have four possible results. Okay, keep that in mind. Now, let's go to our first game. We will be a little more playful. Quantum tic-tac-toe. I guess all of you have played tic-tac-toe. Well, the ordinary version at least. Okay. So you have a board, which is essentially a 3x3 grid. There are two players. One puts X, the other puts a cycle. And the one who made 3 in a row, either horizontally, vertical, or diagonal, wins. Okay. Now, quantum tic-tac-toe. What are the differences? We still have a 3x3 grid, okay, but this grid has a magical property. In each box, there can be more than one symbol. So we can have an X and a cycle, leaving both together, for example, in box number 4. Okay. And whenever I play in my turn, I put two symbols in the board. Let's see. Okay. Now, there's an example. I have a spooky marker. What does the spooky marker do? It allows me to play two symbols in two different boxes. This is a quantum move, and these symbols are in superposition. So, the first player who plays the X, he puts it on the box number 3 and to the box number 5. That means this move is both at the same time, with 50% chance, in both these boxes. Okay. And the second player do the same. Now, what are the rules and restrictions of this game? Okay, here we have the same two moves. The first player put an X on 3 and 5, and the second on 5 and 9. Okay, so we have two quantum moves of quantum tic-tac-toe. The rules are, each player on their turn plays their symbols in superpositions over two boxes, exactly two boxes. Okay, and this move links those two boxes. Now, if these moves share some boxes, there are overlapping boxes, we say that these moves are entangled. Why? Because when we talk about measurements, we will see that there is a correlation between those two moves. And when a closed loop of entangled boxes appear, we must make a measurement. Okay, we will talk about this. Now, very important part. After a measurement, when we talk about it, a grid box can hold only one symbol, either X or the cycle. And this rule also determines how the entangled state works. Okay. Now, let's go. Now, the mathematical description of a move is this one. Okay, now the first player plays and put X in 3 and 5, in boxes 3 and 5. So this move expressed as follows. Okay, with this mathematical expression. What does this say? That the movement, the first move, and I guess that you already noticed it, that every move has an index right down. Okay, this index shows the turn. Okay, so the first turn I write 1, the second turn I write 2, the third turn I write 3, and so on. So, this state shows us that with 50% probability, the move is on the third box, and with 50% probability is on the fifth box. Now, when there are more moves on the board, we get either separable moves or entangled moves. Okay, separable moves are the moves that do not share any box, and entangled moves are the moves that share at least one box. Okay, for example, these two moves are separable moves. Why? Because they don't share any box. Okay. And if we want to write the mathematical expression, is all the possible combinations, okay, with the same probability. So the first, the X is on the 1 and the circle is on the 5th, or the X, the first player on the box 1 and the second on the 9, or the first on the third box and the second on the 5th box, or the first on the third box and the second on the 9th box. So these are all the possible combinations. Okay. Now, if we have an entangled state, there is at least one third box. And what is the mathematical expression that describes this move? This one. And what do I observe? That the possible outcomes are 3, not 4. Because if in the 5th box I make a measurement and I observe that inside this box there is the X symbol, then there can't be an circle symbol. Okay? Because I said earlier, when I measure things, only one symbol takes a box. So if I make a measurement in these two moves, and I observe the X in the 5th box, then I cannot observe the circle on the 5th box, so it has to be on the 9th box. Okay? So all the possible combinations are 3-5, 3-9, and 5-9. Now, if we have many entangled movement, many entangled moves, we say that these moves are forming a chain of entanglement. Okay, like this example. Okay, x1, x1, o2, o2, write down. So when I have a chain of entanglement, these boxes that that has the symbols in them are correlated. Okay. When this chain of entanglement closes, it forms a loop, like the picture right down, then I have to make a measurement. And why do I have to make a measurement? Because when I see a loop of entanglement, or entanglement loop, there are only two possible ways to resolve this when I measure it. So either the green one will happen or the red one will happen. There is no other possible way to resolve this. That means if I measure and observe just one of the moves that participate in this loop, I automatically know the position of the other moves. Okay, so here, for example, if I measure the box number 5 and see that inside the box number 5 there is 04, that means that no other move can be inside box number 5. So x1 must go to the box number 3, and O2 must go to the box number 9. Yes, but if O2 goes to the box number 9, then x3 must go to the box number 7. Okay. So just measuring one of the moves, I automatically know the others. Okay, there is two ways to make a measurement. The realistic one, which is I flip a coin and see with 50% probability which one of the two combinations are true for my case. And the games measurement, where the player that closes the loop, okay, no the player who closes the loop, the next player from the one who closes the loop decides in which box the last move will be when measured. Okay. For example, let's see this case. The second player closes the loop, okay, with a circle, okay, with a no. And then the first player, okay, the first player gets to decide in which of the two boxes, 5 or 7, will be the 04 move. So he decides that it will be on the box number 7. And if 04 is on the box number 7, then O2 must be on the box number 5, X3 must be on the box number 9, and X1 must be on the box number 3. All the moves are resolved together. Who wins the quantum tic-tac-toe? The one who will make a classical tic-tac-toe, 3 in a row. But there is a case that after a measurement, there will be both players will have 3 in a row. So, like this example. Both player with the first player and the second player has a tic-tac-toe. So who wins? The one who wins is the one with the smallest maximum index. So in this case, player number 2, the second player. Okay. Why? Because the smallest maximum index for player number 2 is 6, and the smallest maximum index for player number 1 is 7. sorry, the maximum index for player for first player is 7, and for second player is 6. So the smallest one is 6. Therefore, the second player wins. Okay. So we have some links that you can play quantum tic-tac-toe. We can actually play one game right here.
Yes, you could also play on your phones. There is an application, and you can download it for free. And now we'll make a game with Lazarus here. So you can observe, and then you can play with us if you want. Well, Lazarus, would you like to start?
Okay. I will play here. This has blue dots and red dots. Okay. I will play here and here. So I play my first move, and I put in superposition these two boxes of the grid.
Okay, it's my turn now. I'll play here and in the center box too.
So these two moves are entangled. Why? Because they share a box, the center box, the box number 5. Okay. And I play this one. Now these three moves are also entangled because all the three share the central box.
Okay, let's play here and here.
Now, when Anestis played his move, he closed a loop of entanglement. Which loop? 4, 4, 2, 2, 3, 3. This loop of these three boxes. So, now that Anestis closed the loop, I get to decide where, in which box, the last move will be when measured. So, I will say that this move will be here. So, the 2 red will become larger and take the first box. Oh, the 4, sorry. The 4. The fourth move, the last move. And now this has become a classical tic-tac-toe. And we continue to play.
So it's your move, I think.
Yeah.
Because
Yeah.
you just elected.
So these are two entangled moves, and I will play another one. Here and here. And I close the loop, and Anestis get to decide where.
Yes, I select here to be.
So the last move will be there.
Yes.
That's 7.
7.
And I got a classical tic-tac-toe, so I won the game. If Anestis also had a tic-tac-toe, we will compare the maximum index. So, is anyone who wants to play?
Do we have any volunteers? Okay.
Well, one there.
Yes.
Yes? Come here, come here.
The other guy
And one there?
Who else?
Come. With your insert? Oh, okay.
Hello. Hello. What's your name?
Homer.
Homer?
Yes. Nice to meet you, Homer.
Hello. What's your name?
Now, take the spotlight and play a game. Who will play first?
You want to play first?
Okay? Yeah.
Okay.
Okay, you can play your first move. On 2 boxes. Here.
Yeah.
2 moves.
Every move
Oh.
has 2 boxes in superposition.
It's quantum tic-tac-toe.
Now, these moves are separable or entangled?
They are entangled.
Yes. Why?
Because there are two numbers in one box.
Exactly, because they share a box. Okay? Now,
And I
you
won.
just close. No. Okay, no.
It's
Wait
not.
a minute. You just close an entanglement loop. So the next player, Nicholas, get to decide where the last move will be observed. So the last move was 3 blue. You get to decide where, when we measure this loop, where the 3 blue will be. The first box or the third box?
First box.
You click it. Here.
Okay.
So
And now it's again Nicholas' time.
yes, and now you play.
Because Zart made the measurement.
Another one. Always do. Now, this is also a loop, a small loop, the smallest loop. So you close the loop. So so Nicholas gets to decide where the last move, which was 5 blue, will be when measured. So. Okay.
And
So,
now
you play again.
Oh, yes.
it's your move.
Yes, of course. Now,
It's a loop again.
it's a loop again, and Homer closed it, so Nicholas gets to decide where the last move will be measured. Here. Oh, very interesting. Now,
Who wins?
with the last measurement, we got 2 tic-tac-toes. One for blue and one for red. Who won the game?
I think it's the blue one
The blue one? Why the blue one?
because numbers. There are 3 moves. Numbers.
The microphone.
What we see? We watch for the maximum index. We watch for the maximum index. So, which is the maximum index for the blue? The maximum number. The maximum number. No, in the tic-tac-toe. In the tic-tac-toe. 7. And for the red?
6.
6. Who wants? The one with the smallest maximum index. So the red one wins. That means Nicholas. Congratulations, you won the game. Okay, very nice.
Congratulations to all.
Later, if you want, you can play or you can download the app and play together.
Okay.
Okay, so we continue with the next game.
So, the next game is Quantum Chess. I think most of you have played chess at least once. So, what is a quantum chess? Quantum chess is a quantum version of the classical chess, and it was developed by a graduate student in 2016. You can find it on the Steam online platform. You must pay about 10 euros, I think. But you can play quantum chess for free on your mobile phones. There are some applications. During the game of quantum chess, the concepts you meet from quantum physics is superposition, entanglement, and measurement. As you can see, the quantum chess board, it's the same with the classical chess board. All the moves we can make in the classical chess can also be made in the quantum chess. If you want to make a move in this game, in the quantum chess, you just select the piece you want to move. The piece turns white, and the game gives you the possible positions you can move it. Just classical, as we know from the classic chess. Now, if you want to cancel the move and undo your selection, you just click to the piece again, and you make a new move. What's the difference now in quantum chess? In quantum chess, the quantum move is defined as two consecutive moves made with the same piece. For example, as we can see here, I have on the left down corner the white knight, and if I click it, then I have two possible positions on b3 and on c2. I can make a quantum move. How? Firstly, I click on the first position I want to move it, for example, b3, and then I drag the mouse to the c2 position, and in this way, our white knight is now in superposition between the two positions of b3 and c2 squares. No, I think it's knight. Horse, but okay. But I think in the English is knight. It's not horse, I think so, because I searched on it. Okay, in Greek we say it horse because it looks like horse. But I think in the national literature is knight. So, well, as we can see, we have now our white knight here in superposition in two chessboards. That means that in the first chessboard, the white knight is in b3 square with a probability of 50%. And in the second chessboard, the white knight has moved to c2 position by probability 50% also. So this is it. Now, what's the basic rule in quantum chess? We should also notice. We cannot capture any opponent piece with a quantum move, but only with classical move. What does it mean? It means that if I have, for example, my white knight here in c3 square, I cannot capture the black pawn on d5 position with a quantum move. That is, I cannot put my white knight in superposition and simultaneously capture the black pawn. I must choose either to capture the black pawn or put my white knight in superposition, because I can capture the opponent's pieces only with classical moves. So each piece of the quantum chess can be in a superposition of at most of 65 states. Why? Because a quantum chessboard consists of 64 squares, and we also have one state for the case that our piece is captured. Now, we have also entanglement in quantum chess. How do we meet entanglement in quantum chess? If, for example, I have here my white knight, which is in superposition between the squares b3 and c2. If now the opponent's black knight tries to capture my white knight here, for example, in c2 position, it can attack me to the white knight, but my white knight is not captured by 100%. my white knight has been captured only by 50%. That means that my white knight is still alive, and it's not captured from the black knight here. So now, as we can see in the second image, the two knights are entangled. Why? Because the black one had attacked to the white one, which was in superposition. And when a measurement is made, both of the pieces will be affected, as we see later. Now, when a measurement comes, a measurement is performed when the game sometimes assigns the piece to one of the above squares. For example, as we can see here, and that's the rule of the quantum chess, we cannot have in the same square two pieces of different types. That is, we cannot have in the same square, excuse me, we cannot have a piece which is in superposition and simultaneously to have a piece which is a classic one, which is not in superposition. For example, as we can see here, we have in the second image here, the dark knight had attacked to my white one, as we have seen before. Now, if the white one, which is in superposition, tries to capture the black pawn here on A5 position, a measurement will be performed. Why? To determine which are the positions of the pieces. So, as we can see here, it's in superposition, the white knight, as we said before, and tries to capture the black pawn. The black pawn here is not in superposition. It's a classic piece. So, the converse of superposition can also be made in quantum chess. It's a merging move. And how can we do it? We can merge, for example, the two pieces here. The two white knights are in superposition. Okay, it's on C3 square and E3 square. And now I can merge them. How can I do this? Just I click in one of them and drag it to the second, and I can move them to one of the possible squares on D5 or on D1, just to make a classic move. And now the critical part, when the game is completed. Now, as we know, in the classical chess, when the king of one of the players is threatened, you must move it in order to not to lose the game. In quantum chess, if your king is in superposition between two or more positions, you do not have to move it. So, and that's because the game is completed only when a king, the black one or the white one, is captured by 100%. So, as we can see here in the first picture, we have that the white queen on E6 square threatens the black king, which is in E8 square. So, in the classical chess, you should move your king to continue the game. In quantum chess, you can make to your king a quantum move. How to make a quantum move? You just click on the possible positions and drag it to the second one, and you put your black king into superposition of D7 and F7 squares. Now, the white queen attacks on the black queen, for example, on the square F7. But the game is not completed. Why? Because now the two pieces are entangled. When a measurement is performed, it will make the results, and we see in which positions our pieces are. So, in this moment, in the last picture, as we can see, our king, our black king, is still dead or alive. Just like the Schrödinger cat, you heard about it yesterday and today. So, it's now the time that the king can take his revenge from the white queen, because maybe the black king is not dead, but maybe he is alive. Let's see. Suppose that the black player chooses to capture the white queen to take his revenge. For example, in the first picture here, on D7, the black king tries to capture the white queen here. So, as you can see, the black king, this piece here, is in superposition. So, when he attacks to the white queen, a measurement will be performed. And the system will determine which, in which square the pieces will be found. So there are two possibilities here. In the first case, the capture succeeds. What does it mean? If the capture succeeds, it means that the black king was here in this 7 position. So it was never captured before from the white queen, and he is still alive, and he can take his revenge by capturing the white queen. In the second case, the black king was here in F7 square, which means that the white queen before had captured him, and he was already dead. So the player with the black pieces had already lost the game. Now, there are some puzzles that's for free from the quantum chess. It's the same quantum chess I showed here. And there are some puzzles, you can find them and play. That's for free. And then, if you like it, you can download it and play with others. And you can also download it to your phones. There is a version of quantum chess. It's similar to this. And there is also, for the Marvel fans, maybe some of you know the Ant-Man, and know that the Ant-Man lives in the quantum realm. He can visit it. And there is a very interesting battle between the famous physicist Stephen Hawking and the Ant-Man, the superhero, the fantastic superhero. And the Ant-Man knows quantum chess, and he uses quantum moves so to can win Stephen Hawking. You can watch it, I have the link. And that was another game. Let's continue with one more game here. We will show about quantum bombs and the quantum bomb diffuser. Because what about to tell you that you can deactivate a bomb without leave this world. In the classical case, you could not make it because if you had a bomb and it is active, when you activate it, you will go to the other world. But in the quantum case, in one of the 4 cases, you can be alive. Firstly, we will show here about the virtual lab of the quantum flight trap, because we will present the quantum bomb diffuser here. Virtual lab is a free online application that serves as a simple educational simulation for quantum optics. That's the link here, and it's for free. The main screen of the virtual lab has 3 parts. In the first part here, it consists of all devices and tools you can use. In the central grid here, you can place all the elements and configure the experiments you want. And on the right column, you see all the results and the information about the entanglement and others. There is also here an option when you can find some well-known experiments like Deutsch-Zosa algorithm and others. So now, what is a quantum bomb diffuser? As we said before, it's a thought experiment which was proposed by Ellison and Weidmann. And the goal is to highlight the special effects of non-local correlations that we can have in quantum systems. So here, the experiment assumes that we have here some bombs. Some of them are active, some of them are not active. And we want to detect which of them are active or not. Well, here the experiment setup consists of a bomb, which we do not know if it is active or not. A photon source is here in the place A. 2 photon detectors. The photon detectors here are D1 and D2. 2 beam splitters, which are here the light blue here elements, and 2 mirrors, the purple here. So we wonder if there is any way to check if the bombs are active without making them explode. Because if they explode, we are dead. So how the experiment goes? Here we have the source. The source here emits a photon, and the photon follows 2 paths, which here, the right path and the upwards path, as we say it. And it is placed in superposition between the 2 paths. That is, the photon follows the right path by 50% and follows the upwards path, the upper path, by 50%. Then the photon is leading to the mirrors, and the mirror leads it to the second beam splitter, and the photon is merging here, and it directs to the detector, in this case, to the detector D1. And we also, I missed that we also put the bomb here in the B position, and we don't know if it is active or not. So we sent, as we said here, the photon, and there are 3 possible outcomes. The first outcome is no detector of D1 or D2 is triggered. The second one is that detector D1 is triggered, and the last outcome is that D2 detector is triggered. We consider the orthogonal states here about the direction, for the directions of motion, that the photon moves to the right, and that this one is that the photon moves upward. And we also have a third state here, an orthogonal to the previous 2, which describes the state that the bomb is active, like this here. We suppose that the initial state of the photon is the right one. Here, it goes to the right one. So here we have the relations, and we show that if we set here that as we can see here, the mirrors work like this. They reflect the photon. So if we have the right direction, the mirror directs the photon upwards. And if we have the upper direction, the mirror directs the photon to the right one. Now, when the photon passes through the beam splitter, the photon path is in a superposition of the two initial directions here. That means that the photon is by 50% on the right path and by 50% on the upper path. And here is the process of activating an active bomb. So we have here the first case when we put an inactive bomb. If we have an inactive bomb in the place here B. So we suppose that you have the right initial path here, and because the bomb is inactive, it will not affect the photon's path, which means that the photon will follow all this way, and it will be detected here on D1 detector. That's the case where the bomb is inactive, and there are also the mathematical proofs here, how it is happened. And in the second case, if we have an active bomb, and it is placed here in the B place again, we observe here that the bomb here is playing the role of a photon detector, of a new photon detector, which means that it will perform a measurement to determine the photon's path. If the photon is found in the right path here, so that means that the bomb will explode. And any photon here is detected firstly and then is scattered by the bomb, and it will not detected by either of the detectors D1 or D2. Now, if the bomb does not explode, the photon's path will be the upper one. It means that the photon followed this path. And when it meets the beam splitter, the second beam splitter here, it splits his paths, and it will be found in the 25% of the cases in D1 detector, and in the 25% in the D2 detector. So, what about now the results of an active bomb? We have here, as we can see from the image here, that a photon has scattered and the bomb will have exploded in 50% of the observations here. The second case is that the photon is detected by the detector D1 in the horizontal direction here in 25% of the observations. And finally, the last case is to be detected in the D2 detector here in 25% of the observations. So which are our conclusions here? In the first case, when no photons are detected, the bomb was active and exploded. That means that when no photon can be detected in the detectors D1 and D2, it means that the bomb was active and it was exploded. If the photon is detected in the detector D1, that means that we do not have any conclusion about it, because the bomb might be active or might be inactive. So we must repeat the experiment to make our conclusions. We have uncertainty. But the interesting thing is that when the photon is detected in the D2 detector, and that happens in the 25% of the cases, that means that the bomb is definitely active and it has not been exploded. So that's the most important here conclusion, that in classical world we would not be able to realize it, because if we had an active bomb, when the photon entered our eye to tell us that the bomb is active, we will go to the other world. But in the quantum world, there is a possibility, 1 to 4, that we reach our target and remain alive with a probability, as we said, 25%. And that was the quantum bomb diffuser. So, okay, and we'll finally show you the two games here. Here it's Quantum Sudoku. Quantum Sudoku is a version of the classical Sudoku here. We have, again, here a grid of 9 by 9 squares and 9 boxes with here 3 by 3 sizes boxes. And here is the link we can find and play Quantum Sudoku. Okay, now in Quantum Sudoku, we suppose that each cell is in superposition of all 9 possible states simultaneously, because the numbers are from 1 to 9. A Quantum Sudoku is just like classical one. The cells are not all of them empty. Some of them are already filled. And the superposition of these cells collapse to a number with a certain probability. So this collapse affects the probability spaces of all neighboring cells due to entanglement. And I'll show you an example here in the Quantum Sudoku. For example, here in this box here, we have the possible numbers 6, 8, and 9, which means that this square here is in superposition between the numbers 6, 8, and 9. When a measurement is performed, so for example, here I select the number 8 to be placed here. All the neighboring cells here, that means the cells that are entangled with this one, collapses to their respective numbers, their respective states. What Quantum Sudoku offers us, what's the difference from the classical one? The difference of the classical one is that Quantum Sudoku may have more than one possible solutions, whereas the classical one has only one solution. But we must be very careful how to fill in the squares here, because if we make an unacceptable collapse here, that will lead to a puzzle failure. So the players must think more strategically, and the game is more complicated, so maybe it's more interesting to the players. And finally, I close my presentation here with the Quantum Rock, Paper, Scissors game. I think most of you have played at least once again the Rock, Paper, Scissors, the classical one game. I think that we all know that Rock wins paper, paper wins, Rock wins scissors, scissors wins paper, and paper wins Rock. So let's see how we can make it quantum. Here, a variation of the classical game includes the concepts of superposition and the randomness here. How it is played here, the quantum rock, paper, scissors game. In the classical one, we have 2 players. Each one plays rock, paper, or scissors. In the quantum one, you can make a superposition of all of them. For example, you can play 50% rock, 25% scissors, and 25% paper. A superposition move can make from both players. So when the players reveal their choices, there is not an immediate comparison like in the classical game. The superposition collapses into one of the three options, rock, paper, scissors, based on the probabilities the players chose before. So, and the winning rules are again the same. Once the superposition collapses into a classical choice for each player, the winning rules are the same just in the classical one. What's the difference here? The difference here is that we added superposition and it introduces a new dimension of strategy. So now the players do not play only rock, paper, or scissors, but they can play simultaneously all of them, or a combination, a linear combination of them. So it increases the probabilities for a specific outcome without being absolutely certain. And I'll give you an example and I'll finish my presentation. Firstly, we have two players here, Alice and Bob, and they play the classical version of rock, paper, scissors game. For example, Alice selects rock and Bob selects scissors. The result, of course, is clear. Rock is more powerful than scissors, so Alice wins the round. Now the game is completely predictable as soon as the players reveal their choices. When they show their choices, the game is totally predictable. In the quantum version of rock, paper, scissors, for example, Alice chooses to play 60% rock, 20% scissors, and 20% paper. And Bomb selects to play 50% rock, 30% scissors, and 20% paper. That's superpositions for both of them. Their choices are compared, and the superposition collapses randomly into one of the options based on the assigned probabilities. For example, we suppose that Alice's superposition collapsed to paper and Bob's collapsed to rock. Paper is more powerful than rock, so Alice wins again. And what's the conclusions here? The conclusions here is that the final outcome is determined by the randomness of the collapse, and no one can fully control the result. The strategy is how the players distribute their probabilities in their superpositions. And what we gain from here is that if Bob could read, for example, the mind of Alice and know her preferences in the classical game, but now it's more difficult in the quantum one because there is quantum randomness and the collapse of the superposition, which makes the game more strategic and more interesting to the players. So that was quantum games. Any questions, maybe after the last presentation? And don't forget to play quantum games, guys. Thank you.
Thank you very much. Thank you very much, Mr. Kouspiris. I think that Professor Antoniou wants to make some comments. Please.
Mr. Kosmidis illustrated in a very nice way that there is no cat paradox. You show that the bishop can be at the same time dead and alive. So how to understand this? It was a surprise when Schrödinger published the famous paper, because nobody could accept that a cat can be dead or alive. But now you accept that the bishop is 50% dead and 50% alive. So the only interpretation that is logically acceptable and clear is the famous Aristotelian dynami energia, potentially and actually. It is written in the classical work of Aristotle. So potentiality means what is possible and sorry. And what is in your mind before you decide? This is the Aristotelian potentiality. So here the bishop is potentially 50% alive, 50% dead. When you want to decide about something essential in your life, both possibilities are dancing in your mind before you decide. So this dancing is a superposition of possibilities. That is how you understand, in a very clean way, the so-called Schrödinger paradox and the other quantum weirdness. There is no weirdness. Weirdness is only in our minds that we are stuck in the previous century, mathematics. So concerning Mr. Tsounakis, I want you to think very carefully the last statement about the job opportunities. Quantum computation is an opportunity for future work. There will be many empty positions. And who can get these positions? The physicists. Why? Because they understand quantum mechanics. They are trained in quantum mechanics. And especially, what is now in the forefront of quantum mechanics is the quantum large language models. You know, the deep artificial intelligence, the deep neural networks, all ChatGPT, the Chinese version, the Gemini version of Google, all are deep neural networks. All are based on large language models. What this means? It means that processing in the machine is realized in human language. That is why you don't have to learn computing language, because the computer is understanding natural language. The success of large language models is exactly this, that statement of questions and evaluation of results is done in ordinary language. That is why we don't need programmers anymore. So Bob Koche, who wrote this diagrammatic method that Mr. Sergiologou will present, made a lot of money because he constructed quantum large language models. This is the future, ladies and gentlemen. The combination of present artificial intelligence with quantum processing. And the work of Bob Koche is a milestone in this direction. Yes, this is exactly what he said. Quantum artificial intelligence, which is, as Mr. Tsounakis said, what was artificial intelligence in the 70s. There is a lot of things to come, and there are many challenges waiting for you. The Nobel in physics, as I said yesterday, 1 year ago, was in artificial intelligence because the standard magnetization models, the Ising models, was the basis of the modeling of neural networks. So you see that the last 4 years, everything is converging. Physics is facing a new direction, a new reality. This reality is quantum and artificial intelligence together. This is the big challenge for everybody. Now, concerning Mr. Tsounakis, he said that errors are unavoidable. We are making errors. Machines are making errors. We have to accept this. So, how to resolve the errors? One way to resolve is at the software level. Software level means that you have to add bits or qubits to take into account the correction. You correct the errors by thinking, by creating new possibilities, by eliminating the wrong information. You need more bits for this. And this means that you have to add the so-called logical qubits. Logical qubits are different from processing qubits. Processing qubits, what is minimally necessary. Logical qubits are the bits that are logically necessary to finish the job, plus the bits, the ancilla bits, to correct the errors. A second possibility that he also pointed out is the hardware solution. You make more clever hardware, which is doing the job at the material level. The future will decide what is best. Also, I wanted to clarify a subtle point, the point of computability. Mathematically speaking, solutions exist. You can prove that they exist. But a physicist needs more. A physicist wants to actually construct a trajectory. That is not always possible. Why? Because of complexity. Complexity means limits to computability. What this means? The solution exists, but if I want to construct the solution, if I construct 3 steps ahead, and I need a memory of 100 bits, for the next step, I need 2 times 100 bits. For the 4th, 5th step, I need 2 multiplied by 200. So the growth of necessary memory is doubling at every step. This is the fact of life. We like it or not. This poses significant limits to computability, significant limits to predictability. Mathematically, the trajectory exists. It is one and only one, and it is there. But humans cannot get it. Cannot get it using finite material memories. If God uses the whole universe to make predictions, even God is limited. It's a very simple exercise to demonstrate this for chaotic systems, also for the problems of computability that Mr. Tsounakis mentioned. So the physicist needs the mathematician to prove the existence of a solution, so he doesn't lose his time looking around, but he needs more. He needs the concept of computability. And what we can prove that some problems are not computable systematically. This is the key word, which means there is no universal algorithm from which you can get the answer. But this does not exclude that a clever guy or a guide inspired by the Holy Spirit can see the solution. This is possible. Very improbable, but possible. You cannot exclude that. So as he said, you cannot systematically go there. But somebody may get inspiration and get there. But this strategy is not universal. He cannot generalize the way. He cannot say, I use this way to go there, so you can also do it for the other problem. You can prove that the other problem needs a completely different strategy. And about quantum information, he said that quantum information is lost when I transmit it. Mr. Tsounakis spoke for 1 hour and something. Did he transmit information to us? Yes. Did he lose this information? Mr. Tsounakis, did you forget what you said? No. Which means that what he transmitted to us is classical information. If he transmitted quantum information, he would have forgotten what he said. The bits that he transmitted to us would not be anymore in his brain. Now, he said also that teleportation in the Star Trek sense is impossible. Correct. but Star Trek can have an interpretation as the quantum information necessary to reconstruct the organism. This is imagination, of course. Then you can transmit this information and you can regenerate the teleported person. This is, of course, imagination, but speaking theoretically, if you have this possibility, it is possible to have actual reconstruction. So you transmit the information necessary to reconstruct the being called human body or a stone, whatever. So I think these are exciting questions. Our generation has just understood that something is wrong with classical thinking, that quantum mechanics is much more than the calculation of atomic and molecular spectra and elementary particles. And I was astonished, I was discussing this with Lazarus, how the students, without knowing linear algebra, advanced mathematics, can still play quantum games and understand entanglement in an operational way. Thank you.
Thank you. Thank you very much for your comments, Professor. I would suggest to move on to the next talk. And by the end of the session, we'll have the chance to ask all the presenters whatever you want. So the next talk is from Professor Doctor. Are you a doctor yet? Are you a doctor? You have a PhD? No. Hopefully. Lazaros Arigolis, he will be talking about quantum commutation diagrams, please.
Thank you. Well, the title is Quantum Pictures, Quantum Physics from Pictures. Let's see. Well, I put some slides. I put some slides here to illustrate the things that have already been said in the previous sessions, and that is, in order to start speaking about quantum mechanics in the basic level, you need at least linear algebra. Okay, you need the vector space, you need the basis vectors, the state is a unit vector. Okay, you observe the probabilities, and you observe the axis with some probability, and all this process uses linear operators. So, for example, if you want to measure something, you need a projection operator. The observables are Hermitian operators, etc., etc. So, someone thinks that at least I need to know linear algebra for me to start talking and studying quantum physics and quantum mechanics. But can I explore the realm of quantum physics without using math at all? Well, at least we use some addition. Well, I say I can use diagrams, I can use pictures. And how will you use them? The history of the ZX diagrams, which are the diagrams we are talking about, began with Boolean algebra, and step by step we get closer to what we will talk about today, which is illustrated in the book Quantum in Pictures. Okay, the last one, which is a book our team has translated in Greek and published it here in Greece. It is written by Bob Koike and Stefano Goggioso. and it is exactly the method to make quantum computation without using math, but some rules of pictures. Okay, some pictures and some a rule set with them. So, why we need that? Well, at first it's simple. Okay, it's simple so students without the necessary background, mathematical background, can learn about it. Also, they minimize the computational difficulty. Well, this is a tool that originally developed not for educational purposes, but for industry. Okay, to make processes cheaper, or to make quantum processors better and cheaper. Okay, and a first attempt from the Quantinium group at Oxford shows that students score significantly well on the tests after they exposed to the quantum pictorialism. Okay, all the diagrammatic approach is called quantum pictorialism. So, let's see how to do quantum computations without algebra. Okay, let's talk about the basic notions of our pictures. First of all, we have wires. Wires are basically lines. Okay, wires are lines that are connecting stuff. Okay, we have different stuff, and I have a wire connecting those two. That means that inside the wire there are some particles or some information that goes through. Okay, so when I sketch a line, I called it a wire. I know that something passes through. Okay. For us, it is information. Classical information or quantum information. Okay. Now, we must agree some things before go further. First, the lines, the wires, show the flow of information. Second, we will assume from now on that the information always flows upwards. Okay, it goes from the bottom to the top. Okay, always. Even in the curved lines. This cap line, we will assume that information goes from the bottom to the top. Okay. We will talk about it, what it means to two lines to be connected. Okay. It shows something. What are the properties of the wire? Well, I can bend a wire, I can stretch it, I can straighten it, I can twist or untwist it. It's the same thing. Okay. Well, it's not always the same diagram, but I can do all this stuff. Second notion, the boxes. What are the boxes? The boxes are those places in our pictures where information goes into a box from a wire, something goes in there, and then an outcome pops out of the box. Okay, so in general, there are input wires, okay, a box, and an output wire. Okay. I can have many wires connected to a box, so I can have many inputs in a box or many outputs, or no inputs and no outputs. Okay, I can have many things. And the boxes for us represent linear transformation. All those matrices we were seeing previously, for us are boxes. Okay, just boxes. Now, a box without input, I called it a state. And a box without output, I called it a test. Okay, so states are boxes without inputs, and tests are boxes without outputs. What are the properties of the boxes? Well, the boxes can slide along the wires. So if I have a box, I can slide it along the wire, like the picture done. Okay, right there. Okay, this is box, and goes here. Okay. Now, diagrams. What are diagrams? Diagrams is any arrangement of boxes and wires. Okay. Like this. I have wires and boxes. Okay. Now, equal diagrams. Some diagrams may look different, but essentially be the same. Like this one. This one and this one is the same diagram. Why? Because I took the box with the spade symbol and the box with the diamond symbol. I said earlier I can stretch wires. So I take this and put it there, stretch it, stretch its wires, its input and output. And I did the same for the box with the diamond. Okay. So I have essentially the same diagram, which is a little bit different when I look at it. And if you want to see it clearer, we can color the input and output wires, each one with different color. So I can see that each wire goes, the red wire goes to the spade box, and the green wire goes out the spade box. Okay, pops out. And the same goes for every wire in the diagram. So it's the same diagram. Now, if I have two diagrams who do the same job, okay, or I can transform the one into another with the rules we said previously, we say that they are equal and write the equal sign. Okay. From this I can create diagrammatic equations, just as I use in classical mathematics variables and numbers and create equations, linear equations, differential equations later in university. I can create equations to diagrams. And of course, I can solve them. Okay, I can find some diagrams that are a solution. Okay. For if I put a box with a question mark and say, well, what box does this? I can find a solution. Okay. Now, we have the cups and caps. Okay, so these are the U-shaped wires. I can see those curved wires as boxes. What boxes? Imagine that this is a box, okay, with 0 inputs and 2 outputs. So I can call it a cup state. Okay, it is a state because it has no inputs. Okay, I can imagine that there is a box here. Okay, it has 2 outputs and 0 inputs. Similar, I can imagine that this is a cup test. Okay, because it has no outputs and 2 inputs. These are very important wires because they represent physical system that we can replicate in the industry. Okay. Essentially, this is a bell state. Okay. An entangled state, maximal entangled state. Now, if I combine a cup and a cup, I get a straight line. Okay. How I get a straight line? If I stretch this line, this curved line, I get a straight line. So this equation always holds. Now I can rotate and flip boxes, okay, in a single wires or in double wires. Okay, I can slide the box. And when I try to slide a state or a test, because if it is a state, it has no input, and if it's a test, it has no output, it's like eating the wire. Okay, it's the wire while I try to slide it. Now, we said that with diagrams we can study physical systems. Okay. So in physical systems I have space and time. I have something that happens now, later, happened before, or something that happens here and there. So how do we depict this with boxes? Well, we assume that information always flows upwards. So if I have two consecutive boxes here, A and B, and information goes from down there to up there, first it passes through the box A, and then it passes through the box B. So there is an order in which every box is applied. Okay, first we apply box A, and then we apply box B, where to the output of box A. Okay, like a circuit. And if I have boxes in parallel lines, that means that there are boxes that apply it at the same time in different flows of information, that is, different spaces, different places. Okay, so for us, boxes that are on the same line show us a different time. Okay. They are applied in different time intervals. And boxes that are applied in parallel lines show us that they're applied in different places. Okay. And here is an example of a diagram describing how to make bread. Okay. We have wheat, water, and heat, different stuff. Okay. We grind wheat, we get flour, the first box. Then we have a second input with water, flour and water, and we get the dough after the mixing box. And then the dough with heat, and the baking box, we have the bread. Okay. Simple as that. Here is another example. We have Andre and Blaise. Each one applies 3 consecutive boxes in a different place. Okay, Andre is in one room, Blaise is in another. And what does the cap connecting these parallel lines tells us? It tells us that sometime in the past, these two systems were connected. There was a correlation in the past. Okay, so the connecting lines, the caps, shows us a correlation. Okay. Quantum lottery. Of course, in quantum we have intrinsic randomness. So, well, I want to apply some boxes, but that is not always the case. Some boxes I can apply always, and there are some boxes that there is a chance to be applied. It's like I want to apply this box to my system, but I need to flip a coin and see if I will actually apply the box or not. So we have the boxes that are always applied, and we call them sure boxes, and we have the boxes that are not always applied, and we call them maybe boxes. Okay. If I have a diagram that contains only sure boxes, I have a sure diagram. If I have a diagram that has at least one maybe box, I call it a maybe diagram. Okay. And here is a very important part, that the cap test is a maybe box. So when I want to apply a cap test, I'm not sure that it will happen with certainty. Okay. Now, let's see quantum teleportation. How we can describe quantum teleportation using only diagrams. It's very simple. Okay, what is quantum teleportation? Okay, I have some state here, and I want it to go there. Okay, so I need to stretch a line. Okay, I said earlier that what we can physically use are the cups. Okay, so we can have a cup that goes from one place to another. Andrea and Blaise can share this cup. And if they share a cup, how can they use it to teleport a state, to teleport a box? Well, if I imagine there is a box here, I can slide it through the line and it goes there. Is there a problem with this? Is there a problem? Anyone? Can tell me? There is a problem. What? Do you have a microphone?
Yes.
Ναι, αυτό λέω.
Ναι, ναι.
Here. Now we can hear you.
Maybe because the gray lines show that there was a correlation in the past, but not now. So maybe it cannot pass.
Yes, but I can still slide the box. I'm allowed to do that. Okay. So what's the problem here? There is a correlation in the past, but I can slide things along the lines. Is there a problem? There is. This box is flipped. It's upside down. There is not the box that I initially wanted to teleport. So how can I fix that? Well, if Andrea has this state and wants to teleport it to Blaise, she wonders, what box should I apply here in order for this to work out? And she notices that if I wear a cap in the place of this box here, I can slide this box like this, and we have the teleported state. Okay, so a cap test completes the teleportation diagram, and I'm okay with it. Is there a problem? Yes, because we said earlier that the cap test and most of the tests are maybe boxes. So I am not sure that whenever I want to apply a cap test, this will happen. Okay, so the cap test happens in 1 to 4 times. Okay. So 1 in every 4 times, I have the teleportation diagram I want, and 3 or 4, I have not. Okay. I have an error. Something else, another error box occurs here, so I teleport the state with this error. Can I fix this error? Yes, I can. I can fix this error if I apply, and I say to you this now, the error boxes are flip undoable. What does this mean? It means that if I connect this box with its flipped self, it cancels out. Okay, it's a property of some boxes. And this is a box that has this property. So if Blaise in his part connects it with the flipped error box. It cancels out, so I'm okay. But in order to do that, he needs to know what Alice's error box was. Well, there are 4 scenarios. The error box number 1, 2, 3, or the scenario where no error has occurred. Okay. So, in order to complete the quantum teleportation, Andrea must communicate with Blaise to tell him which error occurred, or if no error has occurred. That is why, in order to teleport quantum particles, we need classical communications. And now we go to the hot stuff. Spiders. Spiders are a type of box and are at the heart of quantum pictorialism. And we will see why. Spiders is a box that extends the idea of wire. A wire has 2 points and connector. Okay, an input and an output. If I imagine a wire that has multiple inputs and multiple outputs, I have a spider. Okay, that's a spider. It's basically a wire with multiple points connecting each other. Okay. Now, spiders are a special case of boxes. Okay, spiders are boxes. They can have many input and output wires, which we shall call them legs. Okay. When we talk about spider legs, there are input and output wires. And spiders have a number on them, an angle, okay, which is the phase. We call it phase. We call it phase. And there are 2 kinds of spiders, the green and the red spiders. That's all. Why the spiders are important? Because by combining those spiders, I can create any box I can imagine. We talked previously about boxes, but we didn't say much. Well, any box you can imagine, any linear transformation, you can create it with these spiders, with red and green spiders. All of them. All of them. Also, they help us to understand when 2 quantum boxes are the same, are equal, do the same job. And of course, we can simplify diagrams with them. Of course, we have spider states and spider tests, okay, because they are boxes. And now we're going to see a set of rules that tells us how the spiders interact with each other. First, spiders with 2 legs are wires. We said that the spiders are a generalization of wire, so a spider with 2 legs is a simple wire. Okay, even if there are outputs, inputs, or input and output. Okay. This works only for spiders with 0 phase. When I don't see a number, I assume that it is 0 angle. Okay. If it has an angle, this is not the case. Okay, spider fusion. I can fuse spiders. If I have 2 spiders with 0 phase here, with the same color, what I do, connecting each other. Okay, here these spiders share at least 1 leg. Here they share 2. Okay, what I do, I merge them together. Okay, so these 2 green spiders become 1, and the total number of output and input legs are the same. So I had 3 legs here and 2 legs there. I have 5 input legs. And so for the output. I can do the opposite job. If I have a spider, I can decompose it, okay, to other spiders. However I like. If I have a phase, then I add the phase. I add the 2 numbers. Okay. And I still do the same thing. flipping spiders. If I flip a spider, I get a spider. And the catch is that if a spider has a phase A, for example, then its flipped version has a phase 360 minus A. Okay. Now, leg chopping. What happens if I have two spiders, zero phase spiders, okay, of different colors that share legs? For every pair of common legs I have, I delete it. Okay, if I have a green and a red spider sharing two legs, I can delete, I can throw it away. Okay. If I have three legs, I throw the pair. Okay, I throw the two, every pair, and I have just one leg at the end. Okay. Here I have four legs, so there are two pairs. I throw them away. First the first pair, and then the second. Here is a p-commutativity. If I have this spider with phase A and a red spider with 180 degrees, I can commute them, and the phase of the green spider gets a minus. Now, I can copy spiders. Okay, if a zero phase spider state or spider test connects by one leg to another spider of the opposite color, then it gets copied. Okay. This example, I have a red spider state, okay, connecting with this green spider that has two outputs. So it gives me two copies of the red spider. This gives me two copies of the green spider state. Okay. These are for zero phase spiders. If I have many more legs, I have many more copies. Also, there is a color change box. There is a box which, when all the legs of a spider have this box connected to them, then the color of the spider changes. Okay. This box has the property to cancel out with itself. If I have a color changing box and a color changing box, nothing happens. Another way to imagine this is I have a color changing box here and a spider. I can imagine this as pushing the color changing box through the spider, which changes the color of the spider, and then pops out from all the other legs of the spider. Okay. For example, this one. I have a color changing box here connecting to this spider in this diagram. I can push it through, so it pops out to the other legs. Then I can continue pushing through these boxes through these spiders. So they change the color of the respective spiders and pops out from the remaining legs. And so I can simplify diagrams or change diagrams if I have color changing boxes. I can see which diagram is equal with what. And there is the square popping. If I have this square, if I counter 4 spiders, 2 red and 2 green, where each of them shares a leg with every other spider of different color, then I can replace this square with a pair of green and red spiders. Okay, this is a rule will not use so much here. So, how all these rules we said connect to bits, gates and circuits we heard from Mr. Tsounakis. Okay. Well,
the red spider state corresponds to the 0 bit. And the red spider state with phase 180 degrees corresponds to bit 1. Okay. So a sequence of bits corresponds to a sequence of spider states. If I have this, I can write it like this in quantum pictorialism. Copying bits. I can copy bits, okay, with these spiders. And then let's start talking about gates. I have the NOT gate. The NOT gate changes a bit from 0 to 1 and 1 to 0. It flips the bit. Which spider does exactly that? This spider. Okay, the red spider with phase 180. Why? Because if I connect this spider state, which is the 0, it becomes 1. And if I connect this, which is 1, it becomes, with spider fusion, 0. The AND gate. If I have this addition, which spider gives me this addition? This one. Why? Because if I plug in the input of this spider 0 and 0, I get a 0. If I plug in 0 and 1, I get an 1 with spider fusion. Okay, the rule of spider fusion. 1 and 0, 1. 1 and 1, 360. A whole cycle, so 0. The phase is 0. CNOT gate. Remember the CNOT gate? CNOT gate does this. If the first bit is 0, is a gate applied in 2 bits. Okay, 2 bits of information. I think in classical it was not CNOT, it was fan out. Yes, it was fan out gate. In classical we have in classical information, if the first bit is 0, then whatever the second bit is remains unchanged. Okay. But if the first bit is 1, then we change the second bit. So if it was 0, it becomes 1. If it was 1, it becomes 0. Okay. So what spider does exactly this thing? This spider. Why? Let's see. If I have this spider, okay, and plug in 0, this is the spider state for the 0, I copy this red spider with this green spider. This is a copy spider, so I have a copy here and here. This is fusion. I have a plain wire and a 0. So the second bit, whatever it was, remained the same because I have plain wire. Whatever input I have the same output, and the first bit is 0. Okay. If I plug in 1 and do the same thing, I see that the first bit remains 1, and the second bit now has the NOT gate, which flips the bit for me. Okay, here are the phase gates. If I have simple spiders with a number, I call them phase gates. Here are some examples of color change boxes through the gates and what happened. There are the same rules. Now, we have an example. We have this circuit here, and I want to plug in this circuit these states. What will happen? Can someone tell me what will happen in this diagram? Has anyone any idea? Well, at first I have some spiders that have the same color. Okay,
this one and this one. What do I do with the same colored spiders? I merge them, I fuse them. So this one with this one, they are fused and become a green spider here and a red spider here. Okay. Also this one. This one will fuse with this one. Okay. Here. Okay. Fuse, fuse, fuse. And we have this diagram. Okay. Then this spider is copied through the red spider. Okay, so I have two green copies. Then I fuse them again, and I have a cup with green, red, and green spider. And here the same. But we said when we have spiders with two legs, are wires. So finally, we get this one. So this diagram is actually this diagram. I made all the computations. These are matrices from linear algebra. We made all the computations by using the spider rules. Okay. And here there are some exercises. And finally, there are many stuff about quantum pictorialism. When we talk about qubits and quantum spiders, we use double wires. Okay. For us, the single wire is the same as an ordinary system, as a classical system, and two wires are quantum systems. We will not dive further into this subject. And here is a quantum C naught. Okay, if I have a C naught is this, a quantum C naught, I double it. Okay. And with quantum wires and ordinary wires, I can have many more examples of quantum encoding, for example. Okay. Where we see that a classical particle goes through there, then I have a quantum particle, and then a classical again. And this is the same as having a simple wire, because I have a bit and then as input and the same bit as output. So it's like having a simple wire. And with this I can beat quantum encryption protocols, but these are more complicated. I just wanted to show you the basic rules of quantum pictorialism so you can go and experiment with some examples and play with spiders, draw diagrams, whatever. So, what is the added value of quantum pictorialism? It doesn't have advanced math. Okay. It's a helpful research tool, and it's easy to understand quantum mechanics. Thank you.
Are there any questions? Yes. Okay, what's the difference between a green and a red gate? How do you say, like, this is green, this is red? Why?
Well, mathematically, it uses a different basis. Wait a moment. Well, wait a moment. Okay. Here is a green spider. Okay. The green spider means that I choose a basis for my vectors, for my vector space, which are these vectors, 1, 0, and 0, 1. And I denote them with ket 0 and ket 1. The red spider does the same thing as the green one, but we have these orthogonal vectors as basis. So they are doing the same job, but they are using different bases.
Thank you.
It's actually a rotation. Yeah, it's a rotation by 45 degrees, exactly. And more specifically, what does the green spider is, I have a spider and I have many inputs and many outputs. Okay. What function, what is spider's main function?